Okay, welcome everybody. We're going to talk about section 8.3 and an introduction to radical functions this time. And our two goals here are to be able to find the domain of a radical function. And the second thing is to be able to graph basic radical functions. So we're going to get into the domains first. And there's a couple of things that we have to recognize. First of all, by definition, a radical function is any function that contains either a variable raised to a fractional power or a variable under a radical. So we have some examples down here below in f of x, g of x, and rx at the bottom of the page. If we're asked to find the domain of one of these kind of functions, the thing that we have to recognize is that there's a couple of definitions that we need. Here's the first one. By definition, right? By definition, if we're looking for an even root, right, we say that the radicand must be non-negative over the set of real numbers. That is, for any nth root, right, our definition is only going to work if our radicand is greater than or equal to 0. So what's the implication of that? Well, let's take a look down at this one down here at the bottom. Okay. F of x is equal to the square root of x plus 7. This is an even root. In this even root, it must be that the radicand is greater than or equal to 0. So in other words, the implication is that to find the domain, we're going to take whatever's under the radical here and set it greater than or equal to 0 to figure that out. Well, in this case, that's relatively easy, because if we subtract 7 from both sides, we get x is greater than or equal to negative 7. So we can put in any number for x, as long as that number of x is greater than or equal to negative 7. In this case, we can write this domain in our set builder notation, the set of all x, such that x is greater than or equal to negative 7. Keep pen. Let's try that again. Greater than or equal to negative 7. Right? Or we could put this in the interval notation, which is to say all numbers greater than or equal to negative 7 to positive infinity. Okay, both of these notations will work equally well. All right, what if it's not an even root? What if it's an odd root? Well, if it's an odd root, we use sort of the same idea, except that by definition for any odd root, the radicand can be any real number. So we're actually have no problems with this piece. We say that g of x, if we have the 1/3 power, remember that x to the 1/3 is the equivalent of our cube root of x. And since we have an odd root, the domain will be any real number. Right? So we could put in the set of all x such that x is in the set of real numbers, which I'll write this way. Okay? Or in interval notation, any number from negative infinity to positive infinity works. All right, quick question. What is this last one right here? We have r of x equals the quantity x minus 4 to the 1/4. Which of these two rules fits? Even root, odd root. That's right. In this case, this is an even root, right? Because we have x minus 4 raised to the 1/4 power. Remembering by definition, this is exactly the same thing as asking for the 4th root of the quantity x minus 4. And so we will want to find a domain of an even root. So we do that by using this rule right here. Whatever the radicand is, we set it greater than or equal to 0 to solve. So we're going to set x minus 4 greater than or equal to 0 to find that domain. Okay, now if we solve that, we're going to get x is greater than or equal to positive 4 in this time. So if we write it in set builder notation, it's the set of all x such that x is greater than or equal to 4. Or in interval notation, square bracket around the 4 to positive infinity. Okay, not so bad.